The main limitation of model-based reinforcement learning technique is that it works only when we know the model of the environment. And by model of the environment, I mean the Markov decision process corresponding to that environment. That is, we know all the states, we know all the actions, we know the transition probability function, and we know the reward function. However, that is not possible for all the reinforcement learning games that we are interested in. For such environment, we are normally given the simulation model of the environment, and the only way to collect information about the environment is by interacting with it. That is, we can learn about the game only by playing the game. So, in that case, we have to use model-free reinforcement learning techniques that do not need information about the Markov decision process. And the most common technique for model-free reinforcement learning is Monte Carlo method. So before I go into the model-free reinforcement learning, let us understand exactly what is Monte Carlo method. The Monte Carlo methods are a broad class of computational algorithms that use repeated random sampling to obtain numerical results like probabilities and expected values. And Monte Carlo methods are often used in physical and mathematical problems where it is difficult or almost impossible to derive probabilities and expected values using basic principles and concepts. So for example, as an application of Monte Carlo method, let us consider this problem of symmetric dice. Now, all of us have done probability problems involving symmetric dice, or which we also call unbiased dice, and corresponding to each of the 6 outcomes for that dice we need probabilities. Now, how do we find these probabilities? For a symmetric dice, we can use symmetry argument and say that because our dice is cubical in shape and cube is a perfectly symmetric object with respect to each of the face, so each of the face will be landing with equal probability. So the probability of any face being on the top will be equal, and sum of all the probabilities should be 1. So using that concept, we can find the probabilities for each of the outcomes, and these probabilities we get as 1 by 6 for each of the 6 possible outcomes for throw of a symmetric dice. Now what if our dice is not symmetric? That is, our dice is unsymmetric or a biased dice. And by unsymmetric dice, I mean each of the face of the dice is an irregular quadrilateral, and the edges and the faces are not necessarily perpendicular to each other. For such an unsymmetric dice, we cannot use symmetry argument to find probabilities for different outcomes, and it will be almost impossible to find the probabilities for each of the outcomes using first principles or basic concepts. So for such case, how do we find estimates of probabilities for each of the outcome? And for that, we use Monte Carlo method, where we perform the experiment. That is, we toss the dice a large number of times, say n, and we count the number of times each outcome shows up. So ni is number of times outcome I shows up. Then we estimate the probability for outcome I is ni divided by n. So using this method, we can find estimate of probabilities for each of the outcome, and here larger the n, that is, more times we throw our dice, more accurate the estimate of our probabilities will be. So this is a simple use of Monte Carlo method to estimate probabilities of different outcomes for an unsymmetric dice. Now, in the case of our reinforcement learning game where we do not know the Markov decision process model, what we do is we play the game repeatedly for large number of times, and in each play of the game we keep track of the states that we are in, the the actions that we take in those states and the rewards that we receive for actions taken in each of the state. And using this information, we can estimate our action value function, that is Q value, and state value function, that is expected value of total present value of the reward for each of the state. Now, the Monte Carlo algorithm for model-free reinforcement learning works along the lines of policy iteration method. That is, there are two main steps. First one is policy evaluation step, where we evaluate the policy, and second is policy improvement step, where we improve our policy. So let's look at the algorithm. In first step, we initialize a policy pi randomly. So what this gives us is an action for each state of our game. In next step, we evaluate the policy, and for that we play the game for large number of times, say n, and for each of the game we start the episode and observe the initial state s, and we take action a according to our policy pi, and we complete the game according to policy pi and observe the total reward that we receive, and this total reward for this episode will correspond to initial state s and initial action a, and we denote that by r of sa, that is total reward for initial state action pair sa. Now for each state action pair sa, we find the action value or q value as average of total rewards r, for which the initial state action pair SA is same as the state action pair SA, for which we want to find Q value. Now once we have the estimate for action value or Q value for all state action pairs, we improve our policy by defining our improved policy as argmax with respect to A of our Q value function for state action pairs SA, and we repeat step 2 and 3 till our policy converges to optimal policy, that is pi star. Now the Monte Carlo algorithm is very easy conceptually, but computationally it is very resource intensive, and therefore there are many shortcomings of Monte Carlo method. The first one is that it is feasible for games that have only small number of states, actions, and they also have small number of steps. That is, the game does not last for long time for large number of steps. And the main reasons for that are, first one, the samples are used very inefficiently because the long trajectories, that is the full game is used to improve only one of the state action pair. That is, by playing the entire game, we are getting the total reward only for one state action pair. Then second, the procedure may spend too much time evaluating suboptimal policies. That is, for a given state S, only one of the actions will correspond to optimal policy and all other actions will correspond to suboptimal policy. But to find the optimal policy, we have to evaluate Q for all the actions available in that state for a large number of times. So that is not very efficient. And also Monte Carlo method works only for episodic problems. So that is also a shortcoming of Monte Carlo method. Now the Monte Carlo algorithm that we just saw is the simplest version of Monte Carlo method, and there are several improved versions of Monte Carlo algorithm that overcome some of these shortcomings, and then there are several other algorithms which combine random sampling concept of Monte Carlo method with recursive relation of model based reinforcement learning to efficiently learn optimal policy. For example, the temporal difference methods like Q learning, SARSA, etc. And these methods we will cover in next sessions.